Hello, my name is Carly Franklin, and this is my submission for Lab 4, Magnetic Field of a Bar Magnet. Introduction. The goal of this lab is to determine the distance dependence of the magnetic field due to a small bar magnet, and then we will be comparing our observational results to our computational results and analyzing the accuracy of our computational prediction. This lab relies on equations that are all derived from the Biot-Savart law, specifically the magnetic field of a dipole and the distance dependence formulas. I set up my experiment using an iPhone application Firefox, a small magnet, and a tape measure. And then I determined the distance in meters to determine all of those values in Teslas for the x component, Bx, of the magnetic field at the location of the magnometer in my iPhone. Otherwise known as, I was looking for the component of the field parallel to the axis of the magnet, which will become more clear in my closed script code. My system is a bar magnet, surroundings, Earth, and everything else. And my initial conditions, I tried to get my x component of the magnetic field Bx as close to 0 as possible. And it was about -1 microteslas. And just a side note, there is some error included in my data because my BNet at this initial point was equal to 252 microteslas. And that indicates that there's an error in my magnometer readings because my BNet was due to my BZ. I'm not supposed to be that high, but let's move on. Here is my Excel datasheet, and this is where I input my results for each of those distances and my Bx values. And I didn't clarify earlier, but I did initially calibrate my magnetic field component at Bx to be 0 because I didn't want any added components from the Earth's field. So now, when I'm looking at my Bx column in this Excel sheet, ideally, those are all contributions from my dipole field and nothing else. And as you can see, there's a little bit of deviation from what the slope is supposed to be, but I got my n is equal to -3.98 loma, and then my I-intercept, -15. And my experimental values obtained through Firefox did not fully align with my computational results, but that's for the discussion. Here I am able to calculate my magnetic dipole moment, mu, or m, as shown in my calculation. And what I did is I took the dipole field equation shown on slide 1 and I simplified it for an on-axis field, and then you took the natural log of both sides of the equation, which is how you linearize your data. And that is the equation shown on the previous slide on my Excel sheet. And then, because of that linearization, you can deduce that -15.8 is equal to natural log of 2km. And then you can do that algebra and solve for your mu. And I got 0.667. And let's go to part 2, coding. Here I have my closed script code. At that red star at the top left is where I input my calculation that I found. And then right below that, that is my equation for dipole B based on Biot-Savart, and then Biot-Savart law. And then what else requires explaining? My D perpendicular, that's for my Excel sheet. It's also what I measured experimentally. And then basically to get all of these different arrows, I just had to basically simulate an arrow at each observation location, and magnetic field vector was calculated using the function with the yellow, shown in the yellow tag. But as you can see, certain arrows are using perpendicular axis, and then other arrows are using the on axis. So it just depends on the observation location. And then it's better shown in my image with the black background. That is how all those arrows panned out with the coding. And then you can see how my computational values and experimental values kind of ended up. And my Bx and By aren't too far from each other, actually, which was surprising. But as you can see, my Bz is where my error lies, and it was an indicator that something bad happened. That I'll talk about right now. Let's see, where do I begin? At 45 degrees, I was not far enough from the magnet, My D perpendicular was about 13.7 centimeters, 0.137 meters. So that led to distorted results and nonlinearity in my Excel graph, specifically due to offset in my magnometer readings, causing my slope to be equal to about -4 instead of -3. So that is the reason why my experimental results do not align with my computational results. And that is really shown in my discrepancy in my BZ. But on the bright side, both my computational and experimental models predict a power law decrease as distance increases, which is the main takeaway of this lab. As dipole strength decreases, distance increases, vice versa, and by a factor of 1 divided by distance cubed. And therefore, the slope for the computational model was perfectly equal to -3, as opposed to my experimental model, which was equal to -4. But I still observe consistent behavior from the dipole in both results. And the main assumptions for my computational model were that the bar magnet is the only source of magnetic field at the observation location, and that I have perfect alignment at B perpendicular, or R perpendicular, R perp, for the observation locations, which is unrealistic, but GlowScript could do it. To continue my discussion, what if I didn't orient my experiment to compensate for magnetic north? This would change my results because my measurements would be larger or smaller depending on the intermediate angle. This is due to Earth's field's contribution to my measured BX and BY magnetic fields, as I mentioned in the beginning of my lab. And this would make my experimental results deviate farther from what they already are, from my computational model, which is what we do not want. So that calibration at the beginning is quite important. Secondly, what if I stuck two magnets together and then redid this experiment? Well, unsurprisingly, my B field at my observation locations would be twice as large because the magnetic dipole moments from each magnet would just add together, leading to everything seeming twice as large, or being twice as large, because there's a magnetic dipole moment that is twice as strong. The end. Thank you for listening.